Okay, everybody, so this will be my last video in a series of videos about power series and how we represent functions by power series. Okay, and just so that that's fresh on your mind, I thought I would mention this example right here. Here's the power series for the function e to the x power. All right, so if you want to calculate e to some power, where e is a Euler's number, E is about 2.718. It's a number used to calculate compound interest and population growths and so on. But all right, but say you want to take E to some power, you could directly calculate that, but since E to the x is also equivalent to this series, you could take 1 plus x squared over 2 factorial plus x to the third over 3 factorial and calculate it that way. All right. So the function in the series are equivalent. They give me different options for calculating e to some power. All right. So now we'll accept that's true. All right. And in general, here's our reasoning and our desires for that. We want to find a way to get a power series to represent a function. All right, we got the function. We want to find a way to get this series. The reasons for that is that doing so gives a method for solving differential equations. All right, I'll give you a little bit of background on that. Here's my differential equations book that I have handy. And like, for example, if you study electric circuits at some point, very often analyzing the circuit and finding what the voltage or the current is at a certain point in the circuit will involve a differential equation. That's a differential equation right there. It's called a differential equation because it involves the derivative of some function. Like that thing right there, di over dt, is the derivative of the current with respect to time. All right, so you can use power series to solve differential equations. All right. Say electricity is not your thing, then I'll just show you this real quick. It says linear systems of differential equations are utilized in many interesting mathematical models of real-life situations. So yes, lots of things in the engineering disciplines and in science involve differential equations in some way. Okay. All right, but now our class is not differential equations. I just want to mention that in passing a little bit, that representing a function by a series gives us a way to solve those types of problems that you encounter in differential equations, okay? All right, and that might be a class that you take at some point. It may be something that you use in whatever field of study you go into. Another thing about it is a power series can reduce a transcendental function to arithmetic operations. And I want you to think about this and have it sink in. To calculate this is not arithmetic. To take e to some power, that is not arithmetic. E is a number that's irrational, 2.718. It goes on and on and on. To take that number and square it is not arithmetic. What is arithmetic? Arithmetic is adding, subtracting, multiplying, and dividing. When you learned arithmetic in elementary school, that's what it was. So by way of this series, I can calculate e to the second power as 1 plus 2 squared over 2 factorial plus 2 to the third power over 3. That's all just arithmetic. It's adding, factorials are multiplying, exponents are multiplying, it's dividing. It's just arithmetic. Okay? So that's another reason. I'll say more about this in my very last problem of the video. Okay? All right. So, but let it stand for now that we want to find a way to represent a function by a power series. All right, that's our goal at the moment. Let's see how we'll do this. We'll do this by formulating something called a Taylor series. Okay? So say you have a function and say you have some initial number. All right? Say a number's of interest to you for what you're doing. Then the Taylor series centered at that number for the function is created this way. It's an infinite series just as you see it by that formula. Okay? All right. Now, as far as that goes, let's say that this symbol is the k derivative of f. Okay? So if we run from k0 to infinity, it's going to be the 0 derivative, which is just the function, the first derivative, the second derivative, a third derivative, and onward. And then it's going to be over 0 factorial. 0 factorial happens to be 1. 1 factorial, 2 factorial, 3 factorial. And it's going to have powers 0 on x minus c, which is 1. 1, 2, 3. So you see how it matches. Third derivative, third power, third factorial. Second derivative, second power, second factorial. All from this, okay? All right, so that's just a formula. That's the Taylor series. If c is 0, then that's called the Maclaurin series. Okay, so if you read or hear about the Maclaurin series, it's just this Taylor series centered at 0. Okay? All right, I'll mention that in case you see it. Now, let's just see that we can do this. Let's just see that if we're given a function and a number, that we can formulate that right there. Let's start with that, okay? All right, so here's one. It says, find the Taylor series centered at 0. And I guess that could also be called the Maclaurin series, but that's just terminology. For the function f of x is e to the 5x power. So here's our formula, okay? And I noticed that for the function I'm given, I've got to use the function, its first derivative, its second derivative, and its third, and so on. And I've got to calculate the function, first derivative, second derivative, at this given number, okay? So the way I do this, I mean, you can do it however you want, of course, is I just make a list of all the stuff I need. Okay, so there's the function. What's the first derivative? F prime. Using the chain rule, that would be 5e to the 5x. Okay, and then what's the second derivative? That would be 25e to the 5x. And what's the third derivative? Now, I don't know how far I'm going to have to go before I see a pattern, but I imagine this is enough, okay? Now, so there's my function, and up to the third derivative, if I can't find some pattern in the series I'm making, then I might need more. So I'm going to put maybe more. Why maybe more? Well, this is an infinite series. And I'm trying to formulate what all this is going to be for this function at that number. So next thing I'm going to do is I'm going to put that number c into the function, the first derivative, the second, and the third. Okay? So let's say that, I'm going to say equals here. And I'm going to say that c is equal to 0. What is e to the power 5 times 0? That'd be e to the 0 power. That's 1. What is 5 times e to the 0 power? That's 5. What is 25 e to, so that's 25. And 125. All right. So I think I have everything I need. So let's take this. Let's take f of c. Whoops. That's this. That's 1. Okay. Then let's take f prime c x minus c. Remember that c is 0. That's going to be 5 x minus 0. Then the next one, f double prime c, that's 25, over 2 factorial x minus 0 squared. Whoops, there you go. And then the next one, f triple prime c over 3 factorial x minus c to the third power. So that's going to be, 125 over 3 factorial x minus 0 to the third power. Run out of room, but you can see it right there. Okay? All right. Now, I do see a pattern to this. It's fairly simple. Here's what I think that we're going to get. If I was going to formulate the whole thing. Now, if I kept going, here would be the pattern. It's going to be 5x over n factorial to the power n. All right? And if I start at 0 and go forever, I'll get this. Let's try it. What if we start with 0? 0 factorial is 1, and 5x to the 0 power is 1. All right? What about next? N is 1. 5x to the first power over 1 factorial. 1 factorial is 1. 5x to the first power is 5x. This is just 5x. I wrote it down, from the formula. But it's just 5x. And then what will I get? So 2 next. Second power, 25x squared over 2 factorial. Okay, that's this. This is 25x squared over 2 factorial. And then 125x to the third power over 3 factorial. This will do it. This will give me that. So here's my Taylor series. Okay, that's all I need. Okay, so I got it. I got the Taylor series for this function centered at that number. Now, okay, let's do another one where the center is different. Let's see. Here we go. Let's do this one. Find the Taylor series centered at 1 for the function natural log of x. Okay. So once again, I want to tell you what we're up against. I need to do all this, okay? For my function, natural log of x, and my number, I need to do f of c, f prime c, x minus c, and so on. So in order to do that, I'll start by finding the function at c, the derivative at c, the second derivative at c, the third derivative, and maybe the fourth one, okay? I just want to do enough of this that I find a pattern. That's all. So let's see. First, I'll start with the function. That is just natural log of x. Then the first derivative. That is 1 over x. Okay? And the second derivative. That is negative 1 over x squared. Then the third derivative. That is 2 over x to the third power. Let's go ahead and find the fourth one. I could put 4 primes, 4 apostrophes if I wanted to. But when we put notation like that, that's not a power. F superscript parentheses k, close parentheses, that's the k order derivative. I'll write it like that. The fourth derivative, that's going to be negative 6 over x to the fourth. Okay? And those do keep going, right? This is an infinite series. I just hope that I'm writing enough of it down to find a pattern to it. Now, let's put in c is equal to 1 into all these because that's how it goes in the formula. C is 1 in my case. Natural log of 1 is 0. 1 over 1 is 1. Negative 1 over 1 squared is negative 1. 2 over 1 to the third power is 2. And negative 6 over 1 to the fourth power is negative 6. So I think that that's probably enough. Let's write this down now. So I got f of c right here. This is f of c with respect to that formula. I've got f prime c. So I've got all the stuff I need there. So let me put it together now. So my Taylor series is going to look like this. Okay. It's going to be f of c, which is 0. Okay. F prime c, which is 1, times x minus c, which is also 1. f double prime c over 2 factorial. That's going to be minus 1 over 2 factorial. And then x minus c squared. That's this one. Okay. And then triple prime over 3 factorial. There's f triple prime c over 3 factorial. X minus c to the third power. And we'll do one more. What's the pattern? 3, 3, 3. And then 4, 4, 4, and so on. So I'll get the fourth order derivative, which is negative 6 over 4 factorial times x minus 1 to the fourth power. Okay, it might take a little getting used to for you, but it's just that formula. If I can find all these derivatives of that given function, I can put that formula together. The issue is I want to find a pattern to this, and I want to write it in series notation. Okay, so here, with a little reducing, here's what it looks like. X minus 1 minus x minus 1 squared. And let's write like 2 factorial. Let's go ahead and that's 2 times 1. Let's just put 2. Okay? And then this one right here. Look at how these cancel. What's 3 factorial? 3 factorial is 3 times 2 times 1. It's just 6. So what I'm looking at here is 2 over 6. That's a 3 then, 2 over 6. So I'm going to write x minus 1 to the third power over 3. Okay. What about this one? What's 4 factorial? 4 factorial is 24. What's 6 over 24? It's 4. So I'm going to get x minus 1 fourth power over 4. Now I think that I am seeing a pattern, and you probably too. Once I reduce this, 1 and 1, 2 and 2, 3 and 3, 4 and 4, 5 and 5, 6 and 6. Another thing, it's alternating. It's an alternating series. Plus, minus, plus, minus. If you weren't convinced the next term is plus, you could find the fifth order derivative and add to this and see what you get. But I'm comfortable with what I'm seeing there. So here's that series in summation notation. Here's the formula for it. It's alternating. Okay. And otherwise, I think I'm seeing x minus 1 to the n power, as n counts its way up over n. And let's start, we'll have to start at 1 and go to infinity. Is this going to do it? Let's try it out. So counting from 1, I'll get x minus 1 to the first power over 1. That's this. Counting, then going to 2, I'll get x minus 1 squared over 2. Then I'll get third power over 3, fourth power over 4. So this will work for that part of it. Do the signs alternate correctly? Well, when I put 1 in, what's negative 1 to the first power? It's negative 1. What's negative 1 squared? It's 1. All right, so my power is off there. It's not alternating the way that I want it to be. So that would be easy to fix, though. Let's see. Let's just do this. Let's put plus 1. That will work. Negative 1 to the power n plus 1. That will give me a positive, a negative, a positive, a negative, and so on. So this will do it right there. All right. So I could use this function, or this series, to represent this function. Okay? All right. Now, I thought I would say a little bit more about that. I really do think, in terms of just doing the math here, it's probably not going to be that difficult for you. Okay? And it's just, if we want a power series for a function, that's the way to do it. All right? If f of x if a function can be represented by a power series, then that power series is going to be this. All right? So if you needed a series to represent a function, then if that was possible, this would be the way to do it. All right? So I thought, well, let's do one more then, okay? Where I want to do an example that is a little bit theoretical, but I wanted to emphasize something about what having that series does for us, okay? So where do we begin? Let me get my first slide that I showed you. All right. Let's see where. So I said in my first slide, I said, well, I could calculate this function through this series. For example, I could calculate e squared this way. And that this is transcendental. It's not arithmetic, but the power series reduces it just to arithmetic. And the reason why I think that that's interesting is think when you use your calculator to do sine or cosine or tangent or logarithm, how does, you might not care about this, you might never wonder about it, but how does the calculator do that? It's not like it has all the answers stored in memory. A calculator really only does arithmetic. Like the circuitry in a calculator, it can add, subtract, multiply, and divide. How is it going to do something like sine or cosine or tangent then? Sine and cosine and tangent, those are transcendental functions. They are not arithmetic, in other words. Okay, so I thought I'd show you an example about how we can use a series to calculate a transcendental function like sine. And I wanted as much as I can for you to see the big picture of this. It turns out that the Taylor series for sine of an angle, so sine of the angle x is x minus x to the third power over 3 factorial plus x to the 5 power over 5 factorial. That's the Taylor series, the series representation of sine of x. You can get this just from this formula if you want to. It's centered at 0, all right? Okay. But really, how do you calculate sine of 10 degrees? What does that really mean? If somebody was manufacturing a calculator to do math for us, how would they program it to do sine and cosine and tangent? Well, we'll go back to what's the first thing you learned about sine, okay? Sine of an angle. Here's what we mean by that. In a right triangle, it's the opposite side's measurement over the hypotenuse. Okay, that's what it really is. How is that happening in the calculator? In the calculator, it's not sketching a triangle and measuring the sides and dividing them. But I thought that I would do it that way for you. I just want to make a point about it. Like if I said, what's sine 10 degrees? I can do it this way. I got my protractor. I measured a 10-degree angle. I measured this side right here to be 6 sixteenths of an inch, and I measured this side to be 34 sixteenths of an inch. So if my measurements are good, and there's always going to be some measurement error when I do this, sine of 10 degrees should be 6 over 34. So I got that, and I rounded it out 3 decimal places. That's 0.176. That's what sine of an angle is. All right, that's how you do it. All right, we take that for granted though, because we just press this button every time we need to find sine of an angle. But that's what it really means. That's what I'm saying. But the power series can reduce that calculation to just arithmetic. All right, if this is the power series for sine, then you can do sine of 10 degrees this way. Now, one catch is, when we use this, that angle's got to be in radians. So, okay, sine of 10 degrees is sine of pi over 18 radians. According to this, that should be pi over 18 minus pi over 18 third power over 3 factorial. And all of that's just arithmetic. This is all just subtracting, adding, multiplying, and dividing. It's just arithmetic. It reduces this procedure of sketching a triangle, measuring the sides, and dividing them. It reduces it to just arithmetic. So watch, we'll do the math. If you want to, you'll get your calculator out. I wrote this series out up that far, even though it's infinite. I wrote it out this far. I'll get a pretty good estimate. If you do the math on that, you'll get 0.176. That's the same thing I got when I drew this triangle and very carefully measured the sides. Okay? So the series gives us another way to do the math. All right? It gives us another way to do calculations. In this calculator right here, I don't know this for sure because I think the design of the calculator is proprietary to some degree, but it does the transcendental functions with series somehow, okay? Because these reduced calculations to just arithmetic. All right. Now, I just wanted to tell you that that's beyond just, going through the motions and writing out this formula, but I wanted you to have a feel for what most of the functions that we take for granted involve and what other option the power series gives us for calculation, okay? All right, so I wanted to brag a little bit. I got the same answer on both of these, okay? Each way I did it. I did it this way with a ruler. I did it this way with the series, okay? I'm curious though, let's do, what does the calculator tell us? Sine of 10 degrees. It's going to have way more precision than I'm going to get in a picture or writing out an infinite series only 4 terms big. I'll get better precision here, but just for comparison, what's sine of 10 degrees? 0.173. So I was only off by like 3 parts in 1,000 when I did it this way and this way. I got really close though to the actual answer. All right, so those are our options. That's what transcendental functions are, and that's how we reduce them to arithmetic. That's one other aspect of what power series representing a function can do for us.